So, welcome everyone to the first lecture on statistical theory for deep learning. My name, as I think some of you at least might know already, is Michael Kohler, and I'm the one giving this lecture. So I'm actually the main actor and the producer of this show here, and because I'm trying to record the lecture again, and I put it on Panopto, so you can get the recording via the Moodle page, but also via my YouTube page. And due to the fact that this lecture is about actual research in statistics, I thought it might be interesting. Although that's one of the reasons why I give it in English, this lecture. So it might be international interesting, and I want to improve the quality of my recording, so get a better sound than otherwise. And I managed to get the sound in my MacBook and get a good sound for my MacBook from the microphone. And then last week I tried, and it was very successful, that I get also the image from my iPhone on my laptop there, and then it was really great. But this needed Wi-Fi, and today there's no Wi-Fi in this lecture hall, so that's the end of, okay. So what I want to say, it's not funny to be a producer. You should stay with the main actor, not getting the producer. Okay, first comment. Second comment, is there anyone here who does not understand German? Yeah, that's great. Then I can continue in English, but I would have continued in English anyhow, so it's fine. But now we have a real reason, and so I told you already, the first reason is that this lecture might be international interesting, therefore I give it in English and put it on my YouTube page. The second reason why I give this in English is that there are some people in this lecture hall which do not speak German, but the third reason is it's part of our new program in data science, which starts in winter, and I would like to use the recording also for this program, so it makes sense already now to give the lecture in English. Also, it's a new lecture. I've never given this lecture before here, so I have to prepare new notes for it anyhow, so it makes sense immediately to make all things in English and in German. Of course, for the exam, you can use also German. The exam will be in English and in German. That's not the problem. Okay, let me start with some organizational comments on the whole thing. You know already what the title of this lecture is. I don't have to write it on the blackboard anymore, but you know already that the lecture is today. So one day is Monday, one times 9:50 to 11:20. And it's in this lecture hall, which is S101 and 04. But what might be more interesting is the second one, is Wednesday, same time, 9:50 till 11:20. A different building, it's in S105 122. What is called the German Altes Maschinenhaus. And as you can see, I will record the lecture also. I was also thinking about the live stream, but I still that I don't have internet. I forget about the live stream. And also it turns out when I was trying the thing to make a recording and the live stream at the same time, both use the Wi-Fi. If I both times use Wi-Fi, then the Wi-Fi quality is not sufficient for both. There's also a practicing course. This starts on April 30. And but there will be some preliminary registration for the practicing course. In addition to you registered already on Tukan, but in Tukan there are something like this morning I checked. There were 72 students registered. And here are 40 students, so there's somehow again. So if you make the groups from the practicing course according to Tukan, I will need 3 groups, 25 students, but in reality it might be 2 groups might be enough. And that's about, well, first problem is that we have problems to find teaching assistants for it, students supervising the practicing course, but more importantly it's also about money. Our department spent about 10% of its budget. That's about, the budget is yearly about 8 million euro, so about 800,000 euro for the practicing courses for the students which we work as a teaching assistant. But if we maybe increase the number of groups by 50%, then you see this will be something like 1.2 million. So 400,000 euro per year, and that's not in the budget, unfortunately. It would make sense because if I make a limit of 25 students, it's basically too big. So if we reduce it, then it might be reasonable, but it's a problem of money. So we will make a preliminary registration that you come to the first group, to the first in the time you have registered for a group. If you were not able to register to any group, then you just choose one of the 2 which are currently open and go there and show up personally. And then the teaching assistant is Alicia Sänger. She's my PhD student. And if you have any questions concerning it, you send her an email. And my teaching students are all, or assistants or PhD students are always happy if they achieve tons of emails. I'm absolutely sure. It's Sänger@mathematiktheorie.de. And I guess she will send you a mood message about the preliminary registration for the course. Okay, the exam are 2 possibilities. Either as an advanced course, then it's oral, it's joined with mathematical statistics, and it's any time after the end of this lecture you schedule the appointment for the exam with me. So I'll give you more details when the end of the lecture approaches, how we make these appointments, because of course I cannot give you all the appointments on the same day. And they are not all days available where I will make exams, but I guess we can agree on some reasonable times. Or as an elective course, then it's only this lecture, and I already very much scheduled it on the last day of the lecture. So on July 17, we just made the written exam. In the hall, this is then the S105, 122, and it's from 9:50 to 11:20. Both times the exam will be based on the list of exam questions, so I will produce during this course a list of exam questions, and I will show you these exam questions during this course, so you will know the questions in advance. And then I will make some written exam out of this. Also make some oral exam. For oral exam, I will just do some random process to select some of the questions which I ask you during the oral exam. This has the advance that you know in advance what I will ask. You don't have to ask other students what I have asked in the past, and maybe they write this up, and there's a collection of list of questions which I have asked in the past, but then sometimes these list of questions are not totally accurate. And then you wonder what I have asked, but the problem was not the question I have asked, the problem was the version of the question you get. You know in advance, of course, I will not, it might be that I modify the questions a little bit, so that I don't post this question word by word, just to avoid the situation where you have reacted on the list of exam questions by a list of exam answers, and you understand perfectly these exam answers, you learn them, but you cannot answer anything around. So it might be that I trivially modify them. Also in the exam for the elective course, the written one, there will be 4 questions. You have to do 3 of them, and at least three of the 4 questions will be from the list of exam questions, and at least 1 of the 4 questions will be from the practice course. Okay, I uploaded already lecture notes for the first 3 chapters, which is approximately half of the lecture on the Moodle page. You can download it, but you can also use here write what I write on the blackboard. Not necessary to have it. Basically, I will use this lecture notes to decide what I write on the blackboard. So it's a little bit, on the one hand, it's a little bit a stupid thing to think, I have the lecture notes and then I come here with my lecture notes, and the lecturer is writing these lecture notes on the blackboard. That's that's a very clever idea. On the one hand, but on the other hand, of course, I could make some kind of beamer presentation about the lecture notes, present you some slides, but I think you won't really learn something like this. This is about, the whole course is about mathematics. You have to understand the mathematics, you have to understand the proof, and therefore it's important that we do this in detail. So of course I won't write exactly the lecture notes on the blackboard, I will write something around it, and then you will see sometimes there are details missing, and these details come in the course. Okay, the practicing course will lead to a bonus. A bonus means that if you have passed the exam, either the written or the oral, then the mark will go up by 1 small step in the marks. So if you have a 1.3, you will have instead a 1.2. If you have a 1.7, you will get a 1.4 if you have this bonus.
1.3.
Excuse me?
1.34.
If you have a... yeah, that's perfectly correct. If you have a 1.7, then you will get a 1.3, because there is no mark 1.4. So it's not always 0.3, it's sometimes 0.4 marks. Correct. Thank you very much. But only if you pass. And there are some requirements. You will get this bonus provided you participate regularly in the practicing course. Participate regularly in the practicing course means that you participate regularly at all weeks except at most 2 weeks when there's the practicing course. So I just say, okay, if you're sick, then you will have 2 weeks where you can be sick. If you are sick for a longer time, then you just need some certificate from a doctor, and you can also extend these 2 weeks. And there you either be present or you show the solutions to the student supervising the course. So you don't have to be present actually. But on the simple thing would be just to be present. And then there will be one of the exercises which you have to hand in for each week, and you will get up to 3 points for it. And the sum of the points you received must be at least 1/3 of all possible points, and also third condition, 1/3 of the points in the second half of the course. Okay, then there is also a seminar for my advanced course, and this seminar was already announced last term, and it's surprisingly or unfortunately already full. Basically it's more than full. I have more students in it than I want. But I want to ask, is there anyone who wants to hear this as an advanced course, who needs a seminar place? Yeah, true. Then you please come after the lecture to the blackboard, and then we discuss what we can find as a solution. Of course, we will find a solution for that. Not sure whether this term or next term or won't be so for it. Okay. And then very important, the requirement for understanding this lecture. Well, you need knowledge in probability theory. Well, it's somehow not surprising. if you think that I'm a mathematics professor, you are in a master class in mathematics, yeah? So it's an advanced course, and then of course there are some things which you know in advance to be able to understand this lecture. And what I mean by probability theory is advanced probability theory, and I want to give you an example. Think about that you have two random variables on a probability space omega A P, so a probability space. A is the sigma field, P is the probability measure. I have two random variables with values x and y. X takes on values in RD1, y takes values in R with exponent D2. Which are random variables. So they are measurable with respect to the sigma field A and the Borel sigma field in RD1 or RD2. D1, D2 are natural numbers. You have a function f from RD1 to RD2, which is measurable, and the real value function with respect to the corresponding sigma, Borel sigma field. You have and you make the whole thing such that two assumptions are satisfied. The first one is the expectation of the absolute value of f of x, y exists, so it's less than infinity. And the second one, the random variables are independent. And what I'm interested in is the average value of f of x, y given the value of y. So I'm interested in this guy, f of x, y, and the conditional expectation given y to small y. Any idea what this is? And that was basically an exam which I have forgotten to give you in my probability course. So you make a conditional expectation of a random variable or of some random object which depends on two random variables which are independent, and you condition on the value of the second one.
It's just the expected value of f of big X and small y.
Yeah, it's the expectation of f of capital X and small y. Of course, not for all y in RDY, because the left-hand side is not uniquely defined, but for py always for y. Almost all y and y was in R2. And if you don't know it, doesn't matter at the moment. But what you need to, what the requirement is, you should know what I'm talking about, and you should understand the proof which I presented now of this one. Okay, if you want to prove this, how do we proceed? Well, first of all, you remember that this conditional expectation of some object given capital Y is equal to small y, that's a factorization of the conditional expectation of this object given capital Y. So actually it's a statement about this one. So it suffices to show the conditional expectation of f of xy given y. What's that? Well, if we try to plug in here the value of y, well, that's wrong here, because then you compute the expectation jointly together on x and y, which is not true. But you can write this one as an integral. If you think about what's this as an integral, you write it with the transformation theorem as an integral with respect to the distribution of x. So that's the integral of f of x, and then you plug in here capital Y, dpx of x. And then in this one you plug in the random variable instead of its value. And that's what we have to show. If you know this one, then immediately from this one you see that this version where you replace capital Y by small y, it's the factorization of it. That's obvious. And this one you can rewrite the integral as this expectation. So that's to show. Now you have to remember what do I have to show that this one. Actually, and this is almost surely, it's not uniquely defined. You have to show that the right-hand side is a version of the left-hand side. What does this mean? There are three conditions. One was it's integrable, which I ignore. The second one is measurable with respect to the distribution of the sigma field generated by y, which is obvious because there is a composition of y and some function, and this function is by Fubini theory measurable. So this will be measurable. So you just have the third condition left, and the third condition was which follows from. You have to show that if you integrate this guy here, the right-hand side, over any set in the sigma field generated by y, then it's the same as if you integrate f of xy over the set. Now, you understand what the sigma field generated by y is. That's just the English word is missing. Anyone idea what orbit is? I know this. Pre-image. The pre-image, thank you very much. It's the pre-image of y. It's a set of all pre-images of y of some sets from the forensic algebra in RD2. So we have to show for all b in RD2, which is my notation for this, the integral over f of x, y, dp, over this set y, pre-image of y, d, is the same as the integral of the right-hand side. Y, dx of x. Okay, that's to show. That's what we have to show. Any questions so far? Now we prove this. This in turn follows from. We start with the right-hand side. I will start with the left-hand side, or I start with the right-hand side. I rewrite this integral over this function of y here as an integral with respect to the distribution of y, which gives you the integral over b and the integral over f of x small y, dpx of x dy of y. You use Fubini to rewrite this iterated integral as an integral with respect to the product measure of the two distributions. So we have the integral over, well, and what was the z here? It's the range of x in 1. So we write the integral over 1 of f of x, y. And we'll write this symbol as a product measure of the two. Then we use the independence. By the independence, we know that the product measure is just the joint distribution. And I can also rewrite this integral. Yeah, and I should write it in a different way. In this way, because I started here with x, and then with y. So you can also rewrite this as the integral over the whole space, and then the indicator function of the z, which basically means the indicator function of the z b evaluated y. I write it in this way: x y times 1 b of y. Y of x y. And then you use the transformation series again and write this as an okay. We want to go over to this place, yeah? I write this as an if you plug in here, capital F of x, y, 1 b of y, b. And then you use that the indicator function of the zb evaluated at the random variable y. That's just 1 if the argument is in the pre-image of y of the zb. So that's you integrate basically over y with exponent minus 1 of b of f of x y to b. And you compare this with the left-hand side, and you see the left hand. And the point I would like to make, this is the kind of knowledge from probability theory you know, and you need for understanding this lecture. Any questions up to that point? Okay, then let's start with the lecture. We start with chapter 1 as introduction. Will be about 2 or 3 lectures. And what we talk about is deep learning. let me say it's a great pleasure for me to give a lecture about statistical theory for deep learning, because since about 7 years, if you have asked me what I'm doing in my research, then I told all the people, well, my research is focused on 3 things. First deep learning, second deep learning, third deep learning. And so actually, it's exactly what I'm doing. It's about 7 years, and in statistics, I was one of the first guys worldwide focusing on this stuff. So it's a special pleasure. Of course, if I talk about deep learning, the first thing which I should tell you is what is deep learning, and I would define it in that way. These are methods which fit deep neural networks to data. There's a collection of methods. If you look in the internet, and you also find a collection of methods from machine learning, are methods which fit deep neural networks. Which fit deep neural networks. Together. And I put the neural in brackets because sometimes it's also not neural, especially recently. So that's also transformer networks. Of course, this doesn't help you not, because next I have to tell you what are deep neural networks. But I'm not doing this at the moment. This will come in the next 3 sections. I will introduce these deep neural networks before I will tell you about applications. The whole thing has been extremely successful in applications. So the whole thing originates from computer science, and I would say it's a kind of revolution in this world. It's changing the world at the moment, and the world we are living in. Do you know about any applications of deep learning which concern your daily life or your life? Anything? Okay, please. ChatGPT. ChatGPT is, and this concerns your daily life. We're talking to ChatGPT all the time. This is the I mean, first, second, third. Fourth and fifth. And fifth is simulation of human conversation. So it's a chatbot based on a large language model, and where also some programs are around which you can actually talk to. So it looks like the computer got some kind of intelligence. And it's not clear at the moment how useful this will be for the future, but it's expected to be extremely useful also for helping people doing their work. At the moment, for example, you can use it if you have to write programs. You can ask ChatGPT to write these Python programs for you, and then you just check the programs, and you don't write them yourself. And then basically you can start programming Python without really knowing Python, because using this or understanding what this routine is doing is much easier than writing it yourself. So it makes your own work more applicable. I heard beginning of this year a talk about GutGPT. GutGPT was some application in medicine in the US, where in the hospital they had introduced some chatbot which actually has given advice to the doctors treating their patients. And it was identifying the patients who are in danger of internal bleeding. So basically, they describe the patients to the chatbot, and then the chatbot shows them some recent results from the literature about whether this patient is at risk or not at risk for internal bleeding. And that might change the world too. Okay, that's one. Anything else? Please?
The standard image folders?
The standard image folder, so you have some kind of image things. And I made here, that's my second thing, I call it image classification. But it's all kind of image which you can treat now on the computer. So the computer understands images. And I don't know, what was exactly the application you were thinking about?
On my mobile phone, the standard image folder, where you can for example, search for specific faces.
You can search for specific faces and so on. Yeah. Image classification would be something that I want to, or maybe an object recognition into images, like an autonomous. If you want to, if sometimes the autonomous driving is successful, which is not yet the case, then you want to see whether the object you have seen on your cameras or on your video are traffic sign and not, and which kind of traffic sign. Such things. But there are many things. I also wanted to show you something as a producer here. I wanted to show you my advanced technology of recording the lecture, and I could have, it was planned that this iPhone is on the very back, and that the image goes into my MacBook, and then you can choose a follow mode on the QuickTime player. And the follow mode means that it makes one picture from the very back of the whole laptop, yeah? But then it automatically concentrates on the speaker in front, so on the guy moving. So if I move from left to right, then the part of the image which is recorded is shifted. That's really great, I think. There are also some applications of images which I'm not sure whether you like them as a human so much. If you think about all these things which you can do in some countries where you supervise the people extremely. So I heard it about Russia. If the people are going to demonstrations, then they got some cameras throughout the town, and then they can identify afterwards exactly who was there. I heard well, this is obviously not an application you want to be involved. There are some applications where you can think about whether you like it or not like it. I heard it from a taxi driver in London when I was a few years ago in London, asking about crimes in London. Is it dangerous to walk around in London? And then he told me, no, there are crimes totally dropped since they installed all kinds of video cameras, and people know that if they commit a crime, they will be on video and the police will find them afterwards. Easily. That's on one hand, it's good, yeah? On the other hand, I heard some more critical things about the recent war between Israel and Palestine. Yeah? If you heard about, they made a checkpoint between North Gaza and South Gaza, and they want to walk through this checkpoint and want to identify who is the terrorist or not, or are there some terrorists about them, and then they ask the people to look up to the sky. And they had some drones flying over them and making some images, yeah? And or also if you heard about this recent scandal in this war about the targets identification, they have this huge database with up to 35,000 potential terrorists of Hamas, and then they have their drones flying around the country looking for images where they've found it. And then of course, if the drones detect this, they don't fire directly the rocket. Instead, they ask the human being to check whether they should really fire this rocket, and the human being, on average, needed about 20 seconds to decide. So you can imagine how carefully they check this, yeah, about 20 seconds. And the basic thing, what I was doing, they were checking whether this photo showed a man or a woman. Because it was wrong if it showed a woman, because there were no women in the database. So, okay, that's a kind of point, but okay, that's something ethically maybe not so easy. Okay, that's great. Any more things? Yes?
Image
image generation and so on. Yeah, I all think the whole thing is an image. And I know, and there's also even a movie generation. Yeah, there was. I think you can search for the first movie written by artificial intelligence, and it even contains a good joke about the one child. So, okay, generating is something right. I didn't have this as a separate point.
Maybe language translation?
Language translation, a kind of machine translation. That was my fourth point. It's natural language processing, NLP, and I think 20 years ago, this NLP had a lot of people working on the linguistic aspects of it, and nowadays the whole field is dominated by people just doing some kind of deep learning and don't understand the language anymore. And this is extremely useful. You can actually have an app on your smartphone, and I think the Samsung Galaxy also had it regularly in it, so that you can call someone, say in France, and make a hotel. If you want to make a hotel reservation, well, no one does nowadays a hotel reservation by phone, but if you want to make a hotel reservation by phone, you can call them and speak German to them, and the phone translates for you in French, which is great, yeah. This was the dream of the middle of 1990 of some programs in NLP, where I wanted to, where they had a big program from the German government, German Research Foundation, DFG, about where I just want to make such a thing with Japan. They want to call the people and automatically translate you. Nowadays you can do it. And there are tons of applications of that. Okay, I have two more. Well, one is related, machine translation, or you can also make a kind of text classification. Which is related to the ChatGPT, the simulation of human conversation. So you can also get some kind of understanding of text. You can search in huge amounts of text automatically. And then I have one more, which was actually occurring for the first time in 2015. Big sensation about artificial intelligence. You have any idea? Any of you have an idea? Connected with Google? Deepfake is that's something which you can do, of course. As you can generate text, you can also generate images, or you can all kind of No, I was something which is very impressive, which computers achieved for the first time.
AlphaZero?
I think it's AlphaGo. Okay. It's mastering of games. And it's about a Japanese game, Go, which is a very complicated game with a lot of rules, and long time computers were not able to do anything about it, or then when they started the first programs with some supercomputer were able to maybe to be as good as an amateur player. But in 2015, Google DeepMind came up with AlphaGo, and the AlphaGo won against the European champion in the Go playing family. And that was a big sensation, because now the computer can play these games better than the human speeds. Okay, that's about applications. Then maybe, why are they so successful? And there are basically two reasons which you can identify easily, and there's also some theoretical reason, but I will just, what has changed in the world that these things come up. The first thing is the availability of huge data sets. We are collecting nowadays more and more data. in connection with the massive increasement of computing power. There's also something which is connected with the kind of methods we are using, these deep learnings, but that will come later in the lecture, at least my understanding of it, how you normally understand it. But somehow in the world there was two changes. You got more and more data which you can automatically collect, and on the same time you got more and more computing power. And then the final thing, I have to explain to you what are the deep neural networks. And there are three different versions which we deal here. Most popular and the first thing is feed-forward neural networks. That's the first, or the basic thing, which already was around in the 1980s. Then the second thing are these networks which are in particularly adapted to image, some kind of dealing with images. These are convolutional neural networks. And the third thing is the thing which is ChatGPT is based on, I think it's till 2017 came up. These are the transformer networks. And the rest of this introduction, I will first introduce all three kinds of networks in three different subsections, and then I will tell you something about how to fit these networks to data. Okay, any questions so far? Then let me make a break for about 5 minutes. So it's now 10:37, so 10:42 I will go on this day. Okay, I would like to go on with the lecture. If you could please stop your conversation. Thank you very much. So we come to subsection 1.1 where I tell you about feed-forward neural networks. By the way, if I write in this size, can you read it from behind? Well, the first point is the neural networks are biologically motivated. And you can ask whether this, critical ask whether this is a good idea or not a good idea. And there was always a joke about from Sputnik, famous statistician, about okay, the people won't try to build planes like birds. Think about it, so they fly with the wings like the birds. But they are biologically motivated, and what they consider, or what they consider as an aim to model somehow mathematically, is the human brain. So we try to mimic the human brain. And I don't want to go into details about how the human brain is working and so on, but you all know it consists of nerve cells. And so you start with a very simple modeling of nerve cells. By some kind of function. And I say, okay, my nerve cell is a function, it gets some two-dimensional input, and it computes a real-valued output. And how does it do it? Well, the input I call O1 to OD, because later on it will be outputs of other nerve cells. And it's just that you compute a linear combination of your input and then you apply a function to it. Function is the activation function, of which is the symbol sigma. And then you have weights, and the weights are W0, some constants, plus W1 times O1 plus UD times OD. And the W1 to WD are real numbers. So the weights. And sigma is a function from R to R. It's the activation function. You have to choose a property, and then you can make an image for introducing what you are showing what you are doing. So you have a constant index, then you have the input O1, O2 until D. You sum the whole thing up and apply some kind of function. This gives you the output. And you send. So this inputs have some connections to the neuron, and the connection is weighted, so you multiply the input by some weights. And that's your output. And for the biological, for the human brain, you know, these nerve cells, they are doing is they send to the next nerve cell some signal if the sum of the inputs exceeds some threshold. And the inputs are weighted, so that's why you multiply it here by some weights W. Then you sum it up. You add the W0 to say where's the threshold, and then you apply some kind of thresholding function. So traditionally, the activation functions make some kind of thresholding. So, sigma is doing some kind of threshold. And what I mean with that, I can define a special kind of function, which is the so-called crashing function. The function sigma from R to R is called a crashing function if it is firstly non-decreasing and it's satisfied that its argument goes to 0 for argument going to minus, its value goes to 0 for argument going to minus infinity, and argument and its function value goes to 1 for argument going to infinity. Function sigma from R to R crashing function. If it is not increasing, it satisfies. It goes to 0 if argument goes to minus infinity, and it goes to 1 if argument goes to. And the most simple example, for instance, of course, is just a function which is 0 up to 0 and 1 from 0 on. Example. Indicator that x is in the closed or half interval from 0 to infinity. So the argument is 1 if x is greater equal 0, 0 else. Of course, this function is not differentiable, which is a problem if you later try on to learn the weights of your nerve cell or a network of nerve cells. And therefore, a popular example of a differentiable expression function this is the most popular of it. Function. That's the so-called logistic expression. That's 1 divided by 1 plus e to the power minus x. This is so-called logistic expression. Yeah. Yeah, actually, by the way, I forgot to mention, you can also ask a question in German, doesn't matter here. German or English.
Also, der Minus 1, wieso ist der als Minus definiert und nicht einfach?
Okay, the question is why the second Linus component 1 is Linus. It's because it's a typing, basically typing. If I would type, it's a writing error. It should be Linus going to infinity. Thank you very much. Let's present here. And that's the so-called logistic expression. But nowadays, mostly that's traditionally for neural networks. This is some kind of expression function, often the logistic expression. Then some years ago, there come a different suggestion that you use here the so-called ReLU activation function, and the ReLU activation function is 0 until 0 and then x identity. It's basically the maximum of 0 and x. ReLU activation function. ReLU is short for rectified linear unit. X is the maximum x. And of course it has nothing to do with, or not really something to do with the original idea of magnitudes are kind of threshold. And then you get some function space, yeah, of this, what you call artificial neurons. But you can imagine this is not a very powerful function space. So if I just make some linear combination of my input and then apply one single function, that's not very powerful. But also your human brain does not consist of one nerve cell. Instead, it's a network of nerve cells. And what you now use, you make networks of these functions out of it. So you use the above function as building blocks. Using the above functions as building blocks. Neural networks model, feed-forward neural networks, model networks of nerve cells. And that's the most important function in the network. Nerve cells, a function of functions. So, and that's what I have to explain next. And if you think about it, how can you do it? Well, you just do such a function, but not just once, many times. And then you use the output as input of analog functions. Let me first draw a picture about the whole thing. So you have your 1, x1 until it's d. And you have your first nerve cell here. And I always draw it this way also. It's not an accurate picture if you use the redo activation function. This one here. And then you make the same thing again. But with new weights. And then you continue and make it many times. And this gives you a first layer of networks. And then you use all the outputs and make the same with the second layer. So that's the so-called first hidden layer. And then you make a second hidden layer. I don't know, do I have to draw a second one, third one, first, second, you can imagine, and then, so you, oh, maybe I make a second one. It's better. Let's see what I'm doing here. Just have to clean the blackboard more often and quickly draw it. So you go in here. You go in here, go in here. Each time with different weights, of course. And each time you have an additional one. It goes in. And then you go on like this. Until that's the second hidden layer. And so on. And then from the very end, you just sum the whole thing up. Also with weights. And that's your output. And that's here. Okay, which kind of number do I have here? Or it should be capitalized. And now you can imagine that I can give you formulas for this, yeah? Easily. And that's what I'm doing next. And of course you have to specify how many hidden layers do you have. That's my capital L. And how many neurons do you have in each hidden layer. And for simplicity I use each time the same number of neurons. I will use small r many neurons. So model networks of nerve functions, and the functions are functions which I call W, URD, UR of before. And now I have to define what the FW is. FW of X. And W, that's the vector of all weights. make a linear combination of the R, of the output of the R neurons, multiplied with some weight, K means the weight level L, and then we have the output of the K neuron in the layer. Now I have to define what these things are. They're recursively defined. W K small l of x. That's somewhere here. It's an activation function applied to a linear combination of the inputs before. So sigma applied in the layer before. I also have R ready. And then I need there shouldn't be K here. Both times K. I use here an I and here a J. And then you need the weight between neuron J in layer L-1 and neuron I in layer L. And that's I denote here by W I J. There is 1 F W J minus 1 of x. And you can imagine L is running from I is running from 1 to R. And L is running from basically 2 until the second. Oh yeah, I've forgotten the highest weight. That should be W 0 minus 1 here. L is running from 2 to capital L. And you have to start with the first layer. So I have to tell you what is F W I of 1. And that's just instead of applied to the R outputs of the previous layer, it's just applied to the D inputs of layer 0. So we have this one is this time running from 1 to D, and it's in W J of 0 minus X, Xj, X, U, X0, 0. That's this one. And I is running from 1 to it. And again, sigma is the activation function. R and N, that's the width of the network. And L in capital N, that's the depth. And if you are talking about deep learning, we are using networks with depth greater than 1. And now you can imagine if you do it this way, the function gets more complicated and also more powerful. So what do I mean with the vector W? The W is the vector of all weights. W. It's in R, this exponent number of the weights consists of all weights. And the weights are, well, the Wijl and the Wijl and W. Okay. And now maybe someone from you can tell me what is capital K then? How many of these weights are there? And it's always ugly to count these weights. It's trivial, yes? But it's ugly to get the right number.
I think the first way would be to sum over all small over the depth, so over all small L in big L,
Yes.
and over all I, and then over all J.
Yeah, but if you sum over all small l, then for L equal 2 to L, it will each time be the same number. And for L equal 1, it will be the same number, so you can forget about the sum and maybe make a product. Has he got it?
Yes, but the size of I and J are dependent on the layer.
Not in my simple example,
Okay.
where each time you have the same width. So I'm simplifying the whole thing, that I'm using each time the same width, and we'll make a remark later on that you can of course use for each layer different width. Yeah. But if I use the same width, then it's a little bit easier. But you are right, you sum up, so you can look at this one. How many weights are here? Well, you see immediately these are for the last layer, these are R weights, yeah? Correct? Yeah. So you start with R. Then you have L minus guys of L minus times, you have guys of this type. So you have L minus capital L minus 1. And now how many weights are there? If you look at this. R plus 1, but you have it R times. Times running R times, yeah? And then for one guy. So you have R times R plus 1 or R times R plus 1. And then for small l equal 1, you have the last one only. And how many do you have for the last one?
D times R? D times R?
D times R, nearly D times R plus 1. Like the bias. No, R times D plus 1. This way. So the R was correct, but the other one is D plus 1. You know, this is the number of weights you have. And now I can introduce the space of functions. Let's give you definition 1.2. This space F and R, and these are all functions Fw. So W is an R, okay. Of all functions defined by and given with a number, so I should put this here number 2. So numbers 1, 2, and 3 of my lecture. Do I have somewhere colors? Yes. That's perfect. Okay. That's 1. That's 2. And that's 3. Defined by 1, 1, 2, 3. Where the topology, that's the structure and the activation function of the networks are fixed. The activation functions of the network are fixed. And the weights vary. This is called the space of V true neural networks with depth L with R and activation function sigma. And see if this just fits here. Space of V forward neural network. With depth L. With R. And activation function sigma. And what we have here is a function space for functions from Rd to R, which is useful if you want to find in your data some kind of structures defined by real value functions. Sometimes you also want to find some structure defined by a function which takes on only the value 0 or 1, or just one of finitely many values. Then you have to modify the output a little bit, but I ignore this at the moment, first point. Then the topology of the network is very simple here. It has each time the same number of neurons in each layer. This of course can be modified. You can also add some kind of skip connections, so that you have connections from one layer not only to the next layer, but maybe from one layer a little bit to the front, or from the input to the front. You can have here, of course, some kind of variant width that you don't have in each layer the same number of neurons that you can modify. And you can also make some kind of sparse connection, so that you say, for some of these connections, I say at the very beginning the weight always has to be 0. And this defines neural network spaces, and one thing we will consider for these neural network spaces is the approximation power, which we will deal with the second chapter. Okay. Okay, but I think the time is already up. So any questions? Maybe one final question from me. Can you tell me what's special about these function spaces? Why should we consider such function spaces?
I've heard in a different module that these functions that we get from the neural networks can be used to arbitrarily well approximate.
Yes, you can arbitrarily develop that. Maybe we will show this in the practicing course. First, second week of the practicing course, you will actually show this. And then in the course, I will show you some approximation results for smooth functions. But that you can make rather easily. I could also use shallow neural networks which have just one hidden layer, and I can prove this without. But what is the magic thing behind it? And so that's one of the reasons of the success of these networks. I think from a theoretical point of view. Can you have any idea? What is nowadays in theory believed to be a magic thing behind this? And of course you cannot know this, but maybe you can guess.
Can be parallelized.
It can be parallelized. Well, that's some kind of computing. That's not some kind of estimation. That's largely overparameterized. That's a different point. That's a kind of for the generalization and so on, and for fitting. No, you don't know this. It's actually a thing which I have proven in the literature, which goes, well, usually these things don't go back to some single person. Yeah? So many people have the same idea in advance, but if you look in the statistics for deep learning, then maybe it's connected mostly with my name, and together with a PhD student of mine, and he also got an award of it in last year from the Chinese government about it. And my favorite saying is about, if you ask me what is special about neural networks, my favorite saying would be, it's the network stupid. So, and that's a modification of the slogan of Bill Clinton for his election against Bush. There it was, it's the economic stupid. But here's the network, because it's the network, which is the magic thing behind. And you can see this in chapter 2. And also a little bit in chapter 4. You can't see it now, but it's the network. Okay, that's all. Thank you very much.